Hi, my name is Amir Shazani bin Muhammad Nazari. I'm from Multimedia University. I'm a student, and I will be presenting a video about research large-scale requirements engineering in complex system. So my topic for the video is large-scale requirement engineering in complex system. So there are 10 articles related to large-scale requirement engineering in complex system. So the first one, what is complex system in requirement engineering? Requirement engineering is arguably the most important activity in the development of complex software and testing system. In experience, no other activity has greater impact on the success of a system development project. Generally, the higher the complexity of the system under development, the more exacerbated the importance of good requirements engineering becomes. In this video, it presents several lessons learned while addressing requirements-related challenges in a large-scale industrial project. High quality requirements are important since they serve as a baseline among multiple teams on the product that needs to be developed and provide a basis for planning, validating, and testing. A system that does not adhere to its requirement or to requirements not aligned with customer expectations will not fit the purpose it was intended for and likely fail. In addition, the cost of correcting errors introduced early in the requirements phase is known to be significantly more expensive than the cost of correcting errors introduced in later stages, which leading to budget or time overruns, possibly even to project cancellation. Requirement engineering. From the article paper, the project from which I derived the lessons presented in the articles was a large-scale complex system development project with more than 4,000 customer requirements. For a system under development, several hundred distributed components had to calibrate to achieve the required functionality, and existing infrastructure and legacy system had to be integrated. For the figure 111V model shown, this adapted to system engineering used in this project. As part of the system engineering processes, the customer requirements were refined into system requirements, where issues such as incompleteness, ambiguity, inconsistencies, or contradictions were resolved. A system architect then created a high-level system architecture and end-to-end workflows and assigned the system requirements to the identified subsystems. For system requirements assigned to software subsystems, more detailed software requirements were created and documented in a software requirements specification SRS. Subsequently, a software architecture was created to satisfy the requirements captured in the SRS. For each of these artifacts, corresponding tests were created. Next is the limitations of current software development methodologies. Today's software development environments are heavily oriented toward traditional software development methodologies as they centralize their activities in a single organization and points of control. Since the teams are first analyze requirement and write their specifications, and then proceed through detailed design, coding, testing, and etc. Whereas in large-scale system, this cycle is unrealistic. Analysis and design methods must accommodate universal incompleteness, imperfection, uncertainty, and non-determinacy in the requirement and process that arise throughout the system development and evolution. Therefore, organizations need a new paradigm of development to support the following activities, which is the first one. Large-scale system includes thousands or even hundreds of thousands of stakeholders, and it's obvious that attendance of all stakeholders is impossible. Next is the diversity of stakeholders comes from different cultures, concerns, policies, business process, those needs way to respond to their different conflict and changing requirements. On the one hand, the relevant requirements for all the such systems and the integration solution must be understood, updated, and transitioned into the architecture. Beside the more flexible the architecture is, the more adaptability of the large-scale system is for the changes in the operational environment. Requirements must be monitored and managed to ensure that no individual or organization can appreciably change the system without understanding and perhaps getting approval from the other participants. Distributed development activities over many organizations thus require new methods for requirements compatibility, verifications, and problems and detections. Continuous evolution in an operational environment where the number of changes is very large and the period between design time and runtime is blurring. Abstracting the system architectures, their interfaces, and the context for evolving and adapting large-scale systems must be dynamic and rapid requirements response to maintain in a situation of large-scale system operational capabilities. And the last one is automatic validation to support continuous testing in real time and non-deterministic behavior. For the third part of the literature is the collisions of system as in large complex system. The key factor that characterizes large complex IT system is that these systems are assembled from other existing and new systems which are independently controlled and managed. Current software engineering research and practice has paid little attention to the issues involved and the most relevant background work comes from the discipline of systems engineering. Systems engineering focuses on the development of system as a whole as defined by the International Council for System Engineering, which is INCOSE. A coalition of systems is a collection of systems that work together, sometimes reluctantly, because it is in their mutual interest to do so. Coalition of systems are not explicitly designed but come into existence when different systems interact according to agreed protocols. Coalitions of software systems make software engineering particularly challenging. Organizations can design dependability into the coalition as there is no overall design in authority, nor can they control the behavior of individual systems. The system in the coalition may change unpredictably, may be completely replaced, and the organization running the system may then go out of existence. Coalition design involves designing the protocols for communication, and each organization using the coalition orchestrate the constituent system in their own way. However, the designers and managers of each individual system have to consider how to make their system robust enough to ensure that their organization are not threatened by failures. The next part is reductionism and software engineering. Software engineering has focused on reducing and managing epistemic complexity. So, where inherent complexity is relatively limited and a single organization controls all system elements, software engineering is highly effective. However, for collisions of systems with a higher degree of inherent complexity, today's software engineering techniques are inadequate. Reductionism is a philosophical position that a complex system is no more than the sum of its parts, and that an account of the overall system can be reduced to accounts of individual constituents. From an engineering perspective, this means system engineers must be able to design a system so it is composed of discrete smaller parts and interfaces allowing the parts to work together. A system engineer then builds the system elements and integrates them to create the desired overall system. As in the figure 1, reductionist assumption and wicked systems, there are three reductionist assumptions, which is the first one is system owners, control system development. The second one is decisions are rational, driven by technical criteria. The third one is the problem is definable and system boundaries are clear. For the last part of the review is the AI based as an example of complex system. Building AI-based complex systems surely goes beyond using specific AI algorithms, and the development itself is becoming more complex since the data needed and algorithms is implemented become dependent. The system generally consists of a variety of subsystems, some of which are data-centric, while others will be model-driven. Part of the challenge of combining such subsystems, as reported, is non-existence of widely used software development paradigm that deals explicitly with autonomous systems. Nevertheless, there is an agent-based software engineering, which is ABSE, being somehow present in AI research for more than 2 decades, which can provide a solid starting point for reasoning about a system as a whole and about the interaction between the various subsystems. ABSE offers a variety of architectural approaches, both for individual agents and subsystems with multiple agents interacting. An intelligent autonomous agent is considered to be a subsystem able to make an acceptable decision about what action to perform next to its environment in time for this decision to be useful. Except from providing the potential contributions from ABSE to requirements for AI, in terms of defining the properties AI modules or subsystems should have, it is crucial to enhance the organization business intelligence and analytics capabilities to support machine learning by providing the following. First one is updating the data organization layer in end-to-end analytics architecture to support data preparation for ML algorithms. The next one is incorporating a SPLC that supports learning models when the organization plans to aggressively build custom ML algorithms and applications. The third one is choosing an ML platform that supports and interoperates with multiple ML frameworks when the organization plans to leverage service providers for commercial off-the-shelf solutions. And the last one is focusing on storage and compute clusters to support ML capabilities. For example, choosing the public cloud over own IT infrastructure. In this video, they will be concluded for conclusions, challenges, solutions, or lessons. So the first challenges is the challenges faced. This section lists some of the challenges that were faced in the project. The first challenges will be larger number of customer requirements. By means, the larger number of customer requirements pose challenge for analyzing, specifying, and managing requirements. The second one is limited formal interface to customer, which means communication with the customer was formal, meaning that official submittal and review processes had to be followed on most issues. This level of formality greatly increased the time required to receive feedback and clarifications from the customer. The third challenges will be management of customer expectations. Since a large and complex system was being developed, but early prototypes of the system were being shown to the customer, expectations of the customer on how far development had already progressed needed to be properly managed. The fourth challenge is changing technology. By means, since the project spanned several years, technological changes during the time had to be taken into account and accommodated. Next is traceability. Full bidirectional traceability was required for all development artifacts, including requirements. Creating and maintaining the traces was a difficult task due to the amount of time and manual effort required. The next challenge is scope change and creep. Scope change and creep is natural and unavoidable in large projects. For instance, due to changes in technologies and processes, the customer requested modifications to some of their requirements. Last challenge is in long-term projects, it is inevitable that team members face in and out of the project, providing easy access to project knowledge for all team members, such as upcoming deadlines, past deliveries, decisions or trade-off taken, and project risk was a challenge. In these 10 articles, there are 3 solution gain in requirement engineering context for large scale requirement engineering complex system, which is the first one is follow documentation standards. By means, the documentation made by one team at one location without any proper standard can be difficult to understand by other teams. Therefore, the documentation standard must be followed. The documentation standards increase efficiency and consistency, especially when the teams are distributed over geographical locations. Industrial standards, for example, IEEE 830 document can be used for documentation. Next is establish effective review process, which is a review is conducted for the detection of errors and deficiencies in the development process. An effective review process can detect the defects early in the development process and thus can reduce the cost for detecting defects. Last is to follow a feature list. Normally, software requirement specifications are organized according to their features. If the features list is not properly managed, this can cause problems later in the development phases. Since in large projects, the teams are distributed over geographically locations, not resolving the complexity of the features can lead to cost and time overrun. For preparing a feature list, a handsome amount of time and effort is required. There should be several meetings with the domain and application experts in order to resolve interdependencies between different features. This table shows that the overview of requirement engineering challenges and recommendation approaches. For example, the requirement activity is stakeholder analysis. So they use the model and tools for stake source using social networks and crowdsourcing. Next is requirements elicitation. The model and tools is data mining and recommender system and k-nearest neighbor algorithm. K and N is used to identify like-minded users with similar rating histories. For the future work for this requirement engineering challenges, to address the fraud drawbacks, future work should find ways to measure and analyze the impact of changes on all the developed requirements. Those ways could utilize data mining techniques for or cognitive computing. In fact, finding more dependent requirements, those are not transferred or being tested stakeholders such as business rules, process, policies or laws requires much work in using knowledge management and text mining techniques to extract such requirements. Still, we seek to find better ways to get final stakeholder confirmation for the analyzed requirements in order to travel the approved requirement to distributed development units. Regarding the challenges in collision system and reductionism and software engineering, the engineering of collision of system involves the engineering of individual systems so that they can work effectively in a collision and the orchestration in configuration of a collision of system to meet some organizational needs. Based on the ideas in the ULSS book and our own experience in the UKLS CITS initiative, we have identified the top 2 problems that define a research agenda for future software system engineering. So the question is how can we model and simulate the interactions between independent systems? By means, to understand and manage collision of system, they need dynamic models that are updated in real time with information from the actual system. They need this model to help make rapid what-if assessment of the consequences of system change operations. This will require new performance and failure modeling techniques where the models can adapt automatically from system monitoring data. However, other engineering disciplines have benefited enormously from simulation and believe that comparable benefit might be achieved for software engineering. The next question is how can system be designed to recover from failure? The answer is a fundamental principle of software engineering is that we should build systems so that they do not fail. This has led to the development of methods and tools based on fault avoidance, fault detection, and fault tolerance. However, as we construct collision of systems with independently managed elements and negotiated requirements, it is increasingly empirical to avoid failure because some failures are ambiguous. Automated systems cannot cope on their own. Human operators have to use information from the system and intervene to recover from the failure of the restore the system. Last is the AI as a example of complex system. So there will be an AI development challenges. One of large organizations with significant experience in AI development conducted a two-phase study with a set of interviews to gather the major topics and a wide-scale survey about the identified topics in order to observe their software teams as they develop AI-based application. They found that various teams have united the new workflow into pre-existing well-evolved agile SE processes, providing insights about several engineering challenges that organizations may face in building AI-based complex systems, which is end-to-end pipeline support, data availability, collection, cleaning and management, education and training, model debugging and interpretability, model evolution, evaluation and deployment, compliance for varied perceptions. Next is optimizing and combining AI development approaches. Embedded system and online companies identifies three distinct approaches to AI-based software development along with the given typical problems that organization experience when using the wrong approach for the wrong purpose. The first one is requirement-driven development. Second is outcome data-driven development. The third one is AI-driven development, which is the organization has a large data set available and use AI techniques such as machine language and DL to create components that act based on input data and that learn from previous actions. The last part is challenges in SE for development, investigating more into software engineering challenges of deep learning. The interpretive research approach in close collaboration with companies of varying size and type has been reported in and U7 machine language projects to identify 12 main challenges that categorized into three areas: development challenges, production challenges, and organizational challenges by means effort estimation, privacy and data safety, and cultural differences. In conclusion, so in this video, I presented lessons learned and challenges for requirement engineering on a large-scale complex system. In this experience, this lesson significantly contributed to the success of the research presented. There are numerous potential directions for future work, since providing full traceability for the large number of artifacts was a challenge, so it is now currently investigating the use of dynamic tracing to facilitate this task. In addition, investigating whether the use of model-driven approaches to requirement engineering and testing can further increase the quality of artifacts and complex systems, while at the same time reduce the required effort and the development of complex system either in AI based be implemented towards facing the challenges in requirement engineering. Thank you.